Hi, my name is Elizabeth DuPre. I'm a new postdoctoral fellow at Stanford University, and I'm so excited to be with you today as part of the Cultivating Open Science Practices in Academic Research and Culture educational course at OHBM 2022. And today, as part of this course, I would like to introduce the idea of reproducible workflows for open data analysis and hopefully motivate you a bit to think about why this could be important or useful in your own work and really provide some tools to structure your exploration in this space if you're interested in either getting started or improving on your existing practices for reproducible workflows. So first, just to sort of situate our discussion, I want to review really briefly one way we can think about the research life cycle, or the ideal way in which we move through ideas as individual scientists and as a research community. So first, of course, we go out into the world and we collect data. As brain mappers, this often means recruiting participants and bringing them to the scanner, or for EEG or MEG data collection. And then once we've collected the data, we need to process it. This, of course, involves some things like short-term data storage, but also it involves running pre-processing analyses, organizing the data in a way that allows us to do that. Then once we have the data in a format that we can actually analyze, we can go ahead and ask our scientific questions. So we can, assess effects of interest or compare different treatments, statistical treatments of the data to examine effects. And then, of course, many of us would say we're done, we have our result, but there's so much more. We then need to publish the results of our study, ideally publishing the data as well, allowing other scientists to access it. We want to preserve the data in some ways, so it's available over time as new scientists come and interact with our work. And then that would actually allow them, or even us in the future, to reuse that data. So we can maybe examine the data, which would allow us to come up with new research ideas, things that maybe weren't previously asked that we could ask for the first time with this data. And then if we see that there's a gap, we could maybe have a planning and design session for creating a new study, which would then motivate us to collect new data, right? And so this whole life cycle is really kind of the idealized representation of how our ideas flow over time and how we can actually investigate our scientific questions. So today's talk, this idea of open data analysis, really touches on three key points within this life cycle. First, on data processing, so how we organize our files and structure them such that they're amenable to pre-processing. Data study and analysis, so how we actually structure the analysis itself. And then finally, data reuse. So how can we make it such that we are drawing on existing data resources to investigate our own questions, and how can we set up our questions in a way to allow that? All right, so if data analysis is this kind of multi-pronged approach to thinking across the research lifecycle, I'd like to suggest that reproducible workflows are a really important part of thinking about how we can make our work easier and more effective in this space to kind of smooth over our transitions, our experience across the research lifecycle. But to suggest this, I need to first define what I'm talking about, right? So what are reproducible workflows? Reproducibility in and of itself is a term that can have different definitions to different people, right? For the purposes of this talk, I would like to suggest that reproducible workflows mean that you can replicate your results with the same data and the same analysis. So to make this a little clearer, this is a really nice 2x2 table from the Turing-Way community. And here you can see that for data and analysis, we can have different combinations of same and different. So you could have the same data set, but you could have two different researchers code a particular analysis strategy, right? So you could say, I have 2 different researchers and I would like each of you to investigate this data set and see if there's a difference in the functional connectivity of a particular network between adults and children, let's say watching a movie, right? So in this case, because it's a different analysis coding on the same data, this would be robust. Ideally, we as a field might be thinking about generalizable, where we can look across data sets, we can ask different researchers to investigate the same question, and we see that the results still hold. But to get to these longer term goals, we really need to focus first on reproducibility. As a field, reproducibility would mean that when we have a particular data set and we have a particular analysis code, excuse me, we could run it and we would see the same results repeatedly, right? And so this seems like a really nice place to start as a field and as researchers when we're thinking about moving towards openness and robust science more broadly, generalizable science more broadly. So if that's the what, that we can replicate the results with the same data and analysis code, and the why I've touched on is maybe good for the overall progress of science. I would say it is, and hopefully if you're attending this educational course today, you might agree. But I would like to make the case today, particularly when we're thinking about adopting new tools or new strategies for moving towards reproducible workflows, that it's also really good for us as individual researchers to be able to take some of these tools and incorporate them into our work. So, you know, there are many different motivations for this, but perhaps the most selfish one from my own experience is the fact that, you know, as scientists, our number one collaborator is always ourselves from 6 months ago, but she doesn't answer emails. So there have been plenty of times when I'm revisiting an old analysis and I have a question, you know, about a particular parameter that was chosen, or I have a question about the way a particular variable was coded. But I can't ask myself from 6 months ago, right? All I can rely on is what's present currently in the code and the data. And so if we design our workflows in a way that can be truly reproducible, this helps to alleviate that concern, because we don't have to worry about in the future, like, oh, am I getting slightly different results than I did when I first ran this analysis because I didn't code something properly, or because I, you know, made a change that wasn't documented. If it's a truly reproducible analysis, I can run it again and again, and I will always get the same result, which is really reassuring. So hopefully this is a bit of motivation for our time together today. And my goal for today is really to provide you with some tools and suggestions for how to move forward in this space, knowing that there's much more than we could talk about in a 20-minute talk. But I hope that this helps to structure some of our explorations moving forward. So first, I'd like to just introduce version control and motivate it as a tool that could improve the reproducibility of your analyses. So again, make it easier such that you don't have to worry about reaching out to your past self or having something that's not documented, right? Until time travel is figured out, version control is a bit easier. Then I'd like to explore some considerations that you may want to take into account when structuring your scientific code. So if you're writing code with the idea that it will be reused, that may be slightly different than code that you just fire off once. And so how can we think about these two kinds of research objects differently? And finally, I would like to point to some open resources for conducting reproducible analyses. And these will vary between, you know, generic guides for setting up your own reproducible analyses, as well as well-honed tools where you can go with particular scientific research questions and they'll go ahead and set up a reproducible analysis for you. So this is sort of the aspirational to the practical spectrum. But first, let's just think about version control. So if you're not familiar with version control, you probably are familiar with a version of version control that's really nicely illustrated in this PhD comic. And the title of the comic is A Story Told in File Names. So here we can see an initial file called test.dat. Then there's a retest, then a retest. And if you've ever experienced something like this before, this is very painful, I assure you, having experienced this. Then there's a ha, and a crap, and a not bad, and a use this one, and then starting over, right? And so this is a bit tragic in terms of file naming, but I think it is really, really useful because many of us have experienced this, right? Where we go through iterations, and without a system for version control, the best we can do is try to semantically document what's happened in the file structure itself. But if you come back to this directory 6 months later, it's not immediately clear. Should I use the file called use this one? Should I use the file called starting over? Doesn't the file called use this one make a bit more sense to use, right? And so this kind of ambiguity can lead to a lot of difficulties later when reapproaching this data or reanalyzing this data down the road, and therefore really hinders the reproducibility. So version control was developed as a system to help alleviate some of these concerns. And how version control works is that it directly tracks changes in plain text files, so in the files themselves, rather than creating and storing duplicate copies. So rather than, as in the previous comic, having many, many copies of the .dat file, all slightly different, instead we have a directory where we'd only have one .dat file, but we would be able to track what had changed on it over time. And there are many different systems that allow you to do version control. Git, G-I-T, is probably the most popular one currently, particularly within the scientific community. And if you've heard of the platform GitHub, this is designed to work with Git, and it provides access to files recorded in Git directly from a web browser. So you can both work with your files locally as well as remotely. And one of the nice things about that is it means you have a system for backups right away, right? So you can access your files across any number of computers. You can access your files. If you lose your computer, it's a really, really powerful system to enhance your workflow and track it over time. We won't have time to go through Git and GitHub today. When I usually teach this, it's like a 3-hour lecture. So I don't want to suggest that you should, know Git and GitHub the moment you approach it. It's a complicated topic and it takes time to learn. But I think that, as in all things, learning the resources to look at and learning a bit of the jargon can really help to lower that barrier and to make it such that you could approach it in your own work. So if you're looking to get started, I would recommend checking out many resources. I have a particular course that I've taught that I would strongly recommend. It also includes many other courses in the description, and you can find it there. So that might be a fun one to play around with. Another option is if you're using the language R, the statistical language R for your analyses, there's a really nice guide called Happy Git and GitHub for the User that I definitely recommend because it talks about how to easily integrate Git and GitHub version control, Git version control, and extensions to GitHub with R-based analyses. The other nice thing, in particular as scientists, is that because so many scientists already rely on these tools, there's some really nice integrations for things that we often need when working with scientific code and data. So, for example, one thing that's really important is being able to cite your code, being able to cite the work that you did and receive acknowledgement for it in some way, right? And so there are systems directly built into GitHub for integrating with Zenodo, which is a service that supplies DOIs, and it can allow you to mint DOIs for new code releases. So let's say you write code for a paper, you can mint a particular DOI, tag a particular code release associated with that DOI, cite it in your paper. And then if other people reuse your code, they can cite your code and show that they used this in their own work, right? And so that's really valuable as a scientist to be able to see what kind of impact your work has had. There are also tools built around Git and GitHub, built on top of some of the associated work that are really, really powerful for tracking your data and how it's changed as a result of analysis. So in particular, a tool called DataLad, which is developed by some of the attendees here at OHBM this year, can record how code changed the data set on which it was run. It also allows you to track changes to data over the time, building on the same system of Git. And so this can be really powerful for situating your own scientific work, because now you can have ways to track not only your analysis, but also how the data you're working or running that analysis on, changed over time, ideally as a result of that analysis code. Okay, so hopefully that motivates you to check out version control, and maybe starting with Git and GitHub because of the resources that are available there. But there are other things that you may be thinking about when you're looking at open data analysis. And in particular, one is how to structure your scientific code. So structuring code isn't easy. It depends often on the conventions of the language you're working in. It depends also on the goals of your particular analysis. So are you writing an analysis workflow? Do you have a particular experimental question that you're just trying to answer and you're writing code to support that? Or are you creating a new tool that you expect will be used by multiple people over time? Will the code you write be used in just your project, one single project, or is it going to be used in this current project and also in future projects that you or your lab mates are running, right? And so in all these cases, because there are different answers, it's hard to say immediately how you should structure your code. One thing that's clear, though, is that documenting what you've done is really, really important. So people often say that good code is self-documenting, and I think that's ambitious. It can be true, right? It's true that good code can be self-documenting, but I find it's always better to describe what you're doing, either as standalone documentation or directly with code comments or both. And I think this is really something that I would say very broadly with scientific code is don't let the perfect be the enemy of the good. I find that oftentimes a lot of us are concerned about putting our code online because we're worried, I don't have any formal computer science training, for example. I know many of us working in this space do not. And so we're worried that our code isn't good enough to share, right? That it's not going to be useful to other people. And so, if you're worried that your code isn't good enough, the fact that you've written code is good enough. You should share the code that you have because that will help other people. And if you can describe what that code was intended to do or what it actually does, then that will help other people to better situate your work and recognize the contributions that you've made. So this is just sort of a general thing for all open data analysis, is avoiding that fear of not being perfect enables us to move forward, and then we can continue to learn over time. And as a community, our standards continue to change, tools available continue to evolve. There's always learning to do, but trying to keep moving forward is what enables us to advance as a field, both to making reproducibility something that we all have, helping us in our day-to-day work and eventually helping us as a field. So if you're interested in structuring your code, as I said, it will depend on your research question, but there are some good coding practices that are generally good to keep in mind when working, right? And so I would just like to suggest that these are all things that you can improve at your own pace. Again, you don't need to wait until you've read all of these resources or learned everything before you go and share your code. If that's the case, then I would never share my code, right? Like there's always more to learn, but I feel like getting started is what's really important. And when you want to keep going, again, there are resources. So if you'd like to review things on your own, if you just want to look through as you have time, there are resources like the Good Research Code Handbook, which overviews a lot of best practices that are currently available for writing scientific code. If you'd like to improve your coding practices at organized events where you have a bit more headspace to really focus on learning, there's summer schools like NeuroHackademy that provide hands-on experience in this space and access to a really supportive network of instructors and attendees, which is so, so important when being on this journey, is that the more you can reach out to your community, the more people you have to ask questions of, the faster we can all learn and really embrace, science as the product of social knowledge, as our interactions between one another as scientists at spaces like NeuroHackademy and conferences like OHBM. And then finally, if you're, you don't want to learn on your own, you don't want to learn at organized events, but you do want to have access to other people, I would definitely recommend communities like BrainHack, because they maintain online forums for asking questions. And they also hold dedicated events throughout the year where you can reach out to other people and get more information. So definitely check all of these out depending on your particular time available, so that you can continue to improve coding practices as we move forward. All right, finally, I just want to point to some open resources for conducting reproducible analyses. And the goal is not to suggest that you need to immediately leap on board with these, but I hope that they help to structure where you're going and maybe provide some sort of aspirational steps moving forward. So first, I find that the most concrete suggestion is to think about structuring our code, think about structuring our analysis code with templates. So Shablona is a project that's out of the University of Washington eSciences Institute, and it's a convenient template that you can use to structure your scientific code so it's open by design. And what I mean by that here is that just from the start of the project, you're structuring your code in a way such that it could easily be shared either with others or such that when you return to it, 6-8 months later, it's very easy to approach and understand. And this isn't the only template available. There are other templates from projects such as Cookie Cutter, for example, and the different templates will depend on your particular needs. So Shablona is really designed for small scientific analyses. Things like Cookie Cutter can be used for scientific analyses, can also be used for data science projects. It really depends on what you need in terms of what template makes the most sense. But grabbing one of these templates and structuring your code to fit within its framework can be a really, really nice step towards creating open data analysis workflows that are reproducible right away. And then as a slightly more aspirational example, I just wanted to point to a tool that's currently available called NeuroScout. And the idea of NeuroScout is that they reuse publicly available data and allow you to design reproducible analyses directly in the cloud that you can then execute, right? So just to show you what this means a bit. So this is the NeuroScout platform. You can get to it just by going to neuroscout.org. And what we can do is we can see that if we view the different data sets, there are a number of data sets that are all available on OpenNeuro, for example, the Grand Budapest Hotel data set. And it's from Visconti Dialeggio Castello and colleagues. And here we have 25 subjects who watch the second half of a movie. But what's great about this is that they've already designed a number of regressors. So this is run through another open tool, fMRI Prep. And they've extracted some features from the stimulus itself using publicly available tools, APIs to things like Google Video and Clarify. And they can then run analyses directly on these things. So if we, for example, go here, we can see as it's loading that based on this, oops, and my computer froze. Sorry about that. No, it had just loaded. Oh well. So let's try a different one. So if we look at, if we look at a particular analysis, if it loads, I'd encourage you to do this on your own. When it does load, what you can see is that you can see the particular predictors that were extracted. You can see, here we go, a design matrix, the time course of how those predictors evolve over time in the stimulus. And then you can even see BID stats models, which is the brain imaging data structure modeling framework for statistical analyses, such that you have a fully reproducible statistical analysis that can be ideally carried across platforms and reported directly in your work to help clarify to yourself in the future and to other scientists exactly what your analysis included. Okay, so hopefully with all of that, I've given you a bit of a sense on how to get started with reproducibility now. Some resources to look at in moving forward to design more reproducible workflows for your open data analysis, and also some examples of either tools that you can use or tools that can serve as inspiration for structuring your own reproducible analysis moving forward. So with that, I just want to thank my PhD advisor, Jean-Baptiste Pauline, my postdoc advisor, Russ Poldrak, everyone on the slide who has been really instrumental in my own open science journey, and my funding, and you, of course, for your attention. So with that, I'll just leave some take-home messages, and I'm looking forward to discussing this with all of you. Thanks so much.